So in this video we continue with solving different problems from section 1.8 and 1.9. So again, you can just pause the video, copy the problem, try to solve it by yourself. If you can do it, great. Then check your answers with me. If you cannot do it, then look at how I do the video, okay? So we already defined the transformation from Rn to Rm. And we're given a set that is linearly dependent, okay? So v1, v2, v3, and v4 are linearly dependent set in Rn. Show that, so we need to prove this, show that the set T of v1, T of v2, T of v3, T of v4 must also be a linearly dependent set. Okay? So let's first check what we're given, okay? Since working since the set v1, v2, v3, v4 is linearly dependent, then what is the definition of a linearly dependent set? There are scalars C1 through C4 such that not all of them 0, such that C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 is equal to 0. This is nothing else but the definition of a linearly dependent set. This is given, this set is linearly dependent. I write just what does that mean. Okay? Now let us apply the transformation to this new vector, okay? To the 0 vector. So we know, because the transformation is linear, since T is a linear transformation, T of the 0 vector gives you the 0 vector, okay? But the 0 vector is the sum of these vectors here. So T of 0 means T of C1 V1 plus C2 V2 plus C3 V3 plus C4 V4. And because this is a linear transformation, this is equal to C1 T of V1 plus C2 T of V2 plus C3 T of V3 plus C4 T of V4. But this sum of vectors, what do we know? It's also equal to the 0 vector because T of 0 gives you 0. Since C1, C2, C3, and C4 are not all zeros. That was in the hypothesis. Not all of them are zeros. Since these scalars are not all zeros, then this relation here between the vectors T1, T of V2, T of V3, and T of V4 is nothing else but the definition of dependent vectors. That means that the set is implied that the set T of V1, T of V2, T of V3, T of V4 is a linearly dependent set. Or simply that these vectors are linearly dependent. Okay. Next problem is a big problem here. So what does it say? Let S and T be linear transformations from R2 to R2. Let S be the transformation that reflects vectors through the x-axis. Okay? and let T be a horizontal shear such that it is defined. What does T do to the vector 1, 1? It brings the vector 1, 1 to the vector 3, 1. The first two questions are: find the standard matrix that's called A of the transformation S, and find the standard matrix of the transformation T that is called B. Okay, so let's answer A and B. So first part A, I'm looking for this matrix A such that S of X is equal to A times X, where X is some two-dimensional vector. And what did I say? Either you can remember what this matrix is, given that the transformation reflects vectors through the x-axis, okay? Or simply you can see what does this transformation do to the standard unit vectors, and always remember that the standard matrix of transformation is going to be consisted of columns that are images of the standard unit vectors under this transformation. Okay, so let's see. It says that S reflects vectors through the x-axis. So let's see. Okay, we have the. Oh, let's see. I'm not going to be able to see this. So. This is E2 and this here is E1, right? I'm just going to remind you, E1 is 1, 0 and E2 is 0, 1. Okay, so this is described as reflection through the x-axis. That means that E1 is going to get reflected to 0, negative 1. So this is T of E2, sorry, that's E2, and then E1 is going to stay at its place, right? So that means that the image of E1 is just E1, 1, 0, and the image of E2 is the vector 0, negative 1. From here, I get the standard matrix of the transformation, the standard matrix of the transformation S. As I said, it's consisted of the columns that are just the images of, the standard unit vectors under the given transformation. Here I made a mistake. It's not T, it's S. Sorry about that. The transformation is called S, so 1, 0 and 0, negative 1. Okay. Now let's do B. Okay. B is defined as the transformation T that sends the vector 1, 1 to the vector 3, 1. It's a horizontal shear. That means that the standard unit vector E1, 0, 1 stays at its place, and the vector 0, 1 gets transformed. So let's see what is going to happen. This is 1, this is 1. So the vector 1, 1 is this vector right here. Okay, that's the vector 1, 1. Okay, as you can see, the vector 1, 1, 1, 1 is equal to E1 plus E2. Okay, under the transformation T, okay, this vector is sent to 3, 1. So 1, 2, 3. this is t of 1 1, which is 3 1. Okay, and this is going to stay as its place. This vector here in a horizontal shear, 1 0 stays at its place. So what is then going to be, how then we're going to define this sum, right? So the vector 3 1 is the sum of the vector 1 0 plus this vector right here. Or simply you can translate this vector back to the origin, and then this vector that didn't move, right? The vector 1 0. And this means what? This means that the vector 0 1, or E2, right? E2 was transformed into this vector here, t of E2, and as you can see from the picture, t of E2 is just the vector 2 1. It's just the vector 2 1. Okay? So from here, t of E1, as we can see, t of E1 stayed at its place, it's just E1. So we have, which is 1 0, and t of E2 became 2 1. And these are the images of the standard unit vectors under the transformation t, which give me the columns of the matrix B. So I have answered part A and part B. We have found the standard matrices of the transformation S and of the transformation T. So now I want to find the standard matrix of the transformation S composed with T, or simply S of T of X. So as you can see, first to a particular vector we apply, to a particular vector X we apply the transformation T, and then to that image we apply the transformation S. We can solve this in two different ways. So part C, I want to find the matrix, so let's call it S of T of X. Let's define it as Cx, some matrix C, and I want to find the entries of this C. Okay, you can do it in two different ways. One of them, now that we know multiplication of matrices, maybe this is even easier. What you can do is that I'm going to remind you that S of X was defined as what? Ax, and A was 1 0 0 negative 1 1 0 0 negative 1. Okay, and then T of X was defined through the matrix B, where B was 1 0 2 1. Okay, from here C is equal to A times B. I'm just going to remind you that the order of the multiplication is very important when we talk about matrices. Okay, so first we apply to a particular vector, we multiply it by B and then by A, so that's why B is to the right of A, and now just multiply this 1 0 0 negative 1 and 1 0 2 1. 1 times 1 is 1, 0 times 0 is 0, so 1 plus 0 is 1. 1 times 2 is 2, 0 times 1 is 0, so 2, 0 times 1 is 0, negative 1 times 0 is 0, so 0, and 0 times 2 is 0, negative 1 times 1 is negative 1. And this is the matrix C. Or another way how you can get the same answer is just look what is going to happen to the standard unit vectors under this composition of matrices. So let's just obtain the same answer by what we have done so far. So I'm following what this composition of transformation will do to the standard unit vectors. So let's say this is E1 and this is E1 and this is E2, my bad. Okay, so first we apply the transformation T, and T was a horizontal shear, right? So this was the vector 1, 1. Okay, so first we apply T, which was horizontal shear, that brings this vector to 3, 1, 1, 2, 3, okay? Okay, and then to this vector we apply the transformation S, which is a reflection over the x-axis. So this new vector right here is S of T of 1, 1. Okay, and as you can see, this vector right here is nothing else but the sum of E1 plus this vector right here So this is the image of the vector E2. As you can see, E1 didn't move when we applied T. E1 didn't move when we reflected over the x-axis. Again, it didn't move. So S of T of E1 stayed E1. Okay. And then E2 from the previous example, we saw that it landed at 2, 1. So this is T of E1, sorry, E2, my bad. Reflected over the x-axis, we get this vector right here. If you just translate it to start at the terminal point of E1, you'll get the same thing. So this is S of T of E2. And how much is this vector? Well, this vector is 2, -1. Okay, so S of T of E2 is equal to 2, -1. And from here, the matrix C that describes this composition of a transformation is going to be E1, which is just 1, 0. And the image of E2 under the composition of transformations, that's 2 and -1. And of course, as you can see, you will get the same answer. And problem D was find a non-zero vector v1, v2 such that when we apply the transformation S on it and we apply the transformation T on that vector, we get the same vector. Okay, so S of v1, v2 is equal to the standard matrix of transformation is A1, 0, 0, -1 times v1, v2. If you do this multiplication, that's v1, and then 0 times -v2. On the other hand, T applied to this vector v1, v2 is equal to 1, 0, 2, 1 times v1, v2. So that's v1 plus 2v2, and then 0 times v1 plus v2. Okay, so what do we want? We want a vector such that these two will be equal. We want a vector v1, v2 such that when we apply S to it, and when we apply the transformation t to that vector, we obtain the same vector. So basically we want these two vectors to be the same. v1 negative v2 to be equal to v1 plus 2 v2, and here v2. Okay, so from the second entry, what is the only number such that multiplied by negative 1 gives you the same number? For what number negative v2 will be equal to v2? Well, that's only the number 0, so v2 is equal to 0. Applied that to the first entry, v1 is equal to v1 plus 2 v2, v2 is 0, I get v1 is equal to v1, which implies that v1 can be any real number and v2 has to be 0. So v1 v2 is equal to any number k and 0 such that k is a real number. Okay, question 8. Transformation from R2 to R2 is given such that the transformation to the vector xy is equal to the product of this matrix here and these two matrices, right? So the question is this transformation linear? In order for a transformation to be linear, as I said, we have to confirm that the following two conditions are satisfied. That t of the 0 vector gives you the 0 vector, so that's 1, and 2, t of c plus v plus c1 plus v plus c2 times u is equal to c1t of v plus c2t of u, so that these two conditions are satisfied. Okay, so let's start with the first one. So we check if t of 0 is equal to the 0 vector. Okay, so t of the 0 vector is just the vector with entry 0, 0. Now we follow this formula. So when x is 0, I get a 0 here for x, so 1, 2, 0, 1, times y appears in the second vector, so y and 1, so y is 0, 0 and 1. And let's see whether we get the 0 vector. 1 times 0 is 0, plus 0 times 1 is 0, 0 plus 0 is 0, sorry, yes, 0 plus 0 is 0, very good. And 2 times 0 is 2, 2 times 0 is 0, plus 1 times 1 is 1, so 0 plus 1 is 1, which is obviously not equal to the 0 vector. Hence, since one of these two conditions is not satisfied, hence t is not a linear transformation. We don't need to prove or check whether the second condition works or not. If the first one is not satisfied, we just conclude that t is not a linear transformation. Okay, so let's see problem 9. The transformation t takes vectors from R3 and brings them to R3, and it's defined such that t of any vector in 3 dimension x, y, z is defined as x times negative 3, 1, 2 plus y times negative 1, 0, 1 plus z times negative 2, 2, 0. The first question, find the standard matrix A of the transformation T. Second question, give a non-zero vector from the kernel of T. So here we're going to remind ourselves what the kernel is. Describe the set kernel of T. Part D, the question is T onto? E, describe the range of T, and F, find a matrix B of rank 1 such that if the transformation S is equal to Bx, then the standard matrix of this transformation S composed with T is the zero matrix. Sorry. So let's do A. Okay. So how it is defined, T of x, y, z is equal to x, negative 3, 1, 2, plus y, negative 1, 0, 1, plus z, negative 2, 2, 0. And then from this, let's call it a vector equation, we go into the matrix equation, right? So where these three vectors are going to be the columns of our matrix 3, negative 3, 1, 2, negative 1, 0, 1, negative 2, 2, 0, times, let's call these the weights, which are just going to be the entries of our vector, right? And what do I get? I get a matrix A times the vector x. Okay, so obviously A, the standard matrix of transformation, is just negative 3, 1, 2, negative 1, 0, 1, negative 2, 2, 0. A very, very simple question. Okay, now we have to find a non-zero vector that belongs to the kernel of T. So let us remind ourselves what the kernel of T is. The kernel of T is the set of all the vectors. So part B, the kernel of T of the transformation T is the set of all the vectors x such that T of x is equal to the zero vector. Okay, so T of x was defined as A times x, right? Where A, we answered in part A, was the matrix negative 3, 1, 2, negative 1, 0, 1, negative 2, 2, 0, times x is equal to the zero vector. But find x, find all the x's that satisfy this homogeneous system. So what do we have to do? We just have to solve this homogeneous system 0, 0, 0. I'm going to move the first row 1. I'm going to flip row 1 and row 2. 1, 0, 2, 0, 0, 0, negative 3, negative 1, negative 2, 2, 1, 0. Okay, here I have row 2 plus 3 times row 1 becomes row 2, and row 3 minus 2 times row 1 becomes row 3. 1, 0, 2, 0. Negative 3 plus 3 is 0. Negative 1 plus 0 is negative 1. Negative 2 plus 3 times 2, 3 times 2 is 6. So 6 minus 2 is 4. 0 minus 0 is 0. And then 2 minus 2 is 0. 1 minus 0 is 0. 0 minus 4 is negative 4 and 0. 1 minus 0 is 1, sorry. Okay, and now if you have row 3 minus row 2 becoming row 3, we get the matrix 0, 1, 0, 2, 0, 0, negative 1, 4, 0, 0, 0, 0, 0. Or just multiply the second row by negative 1, 1, 0, 2, 0, 0, 1, negative 4, 0, 0, 0, 0, 0. Okay? So these are some entries for x, y, and z. As you can see, z will be a free variable, so z is equal to t, y is equal to 4t, and x is equal to negative 2t. So from here, all the x's that satisfy this equation, or in other words, if you observe this through the lines of transformation, all the vectors that are sent to the zero vector through this transformation are the vectors negative 2t, 4t, and t, or simply t, negative 2, 4, 1. Okay, and then part B says give a non-zero vector. So give a particular vector from the kernel of t. Here, infinitely many vectors are described. If you let t is equal to 1, then one particular vector would be negative 2, 4, and 1. Okay? Now, part C says describe this set. Part C says describe the kernel of t. What does it represent? So, if you look at this equation here, so C, since x is equal to t, negative 2, 4, 1, which is nothing else but the kernel of t, it means that the kernel of t is a line, obviously in R3, it's three-dimensional, that passes through the origin. Why? Because I'm not because when t is going to be equal to 0, I will get 0, right? X will be equal to the origin. Okay. So the question is now, is t onto? Okay. D. So the matrix, standard matrix of transformation, which was negative 3, 1, 2, negative 1, 0, 1, negative 2, 2, 0, got row reduced to 1, 0, 2 in the previous problem, 0, 1, negative 4, 0, 0, 0. So by that very useful theorem 4, since not all the rows of A are, since not all the rows of A are pivot rows, this implies that the columns of A do not span R3. And if the columns of A do not span R3, that means that there are some vectors in R3 that are not linear combination of these three vectors, which means that T is not onto. Okay, or simply T is not onto because the rows of A are not all the rows in A are pivot rows, which means that the columns of A do not span R3. Okay. Now for part E we have to work a little bit. Part E says describe the range of T. Okay. So part E, we want to see what the range of T is, okay? Or we find the set where all the vectors, all the images under the transformation of T land, right? All the vectors from the domain are mapped to, okay? So we want to find b, b1, b2, and b3 such that t of x is equal to b. Okay, but t of x is defined as a times x, which is equal to negative 3, 1, 2, negative 1, 0, 1, negative 2, 2, 0, times x is equal to the vector b, which is b1, b2, b3. And now you have to find the entries of x. So again, you have a system. Here I'm going to give you you will follow the same row operations as when you were row reducing the homogeneous system. So I will skip that part. Negative 2, 2, 0, b1, b2, b3, and then you will get 1, 0, 2, 0, negative 1, 4, 0, 0, 0, and here you have b2, b1 plus 3b2, and in the last row b1 plus 3b2 plus b3 minus 2b2. Okay, so when would this system be consistent? The system is going to be consistent when this entry is going to be 0, right? So it is implied that b1 plus 3b2 plus b3 minus 2b2 is equal to 0, or simply b1 plus b2, right? I'm adding these two entries, sorry, these two numbers, plus b3 is equal to 0, or simply x plus y plus z is equal to 0. But what is this? This is nothing else but an equation of a plane that goes through the origin. Okay, so this implies that the range of the transformation t is a plane through the origin. Given by the equation x plus y plus z is equal to 0. And at the end, the question is, find a matrix B of rank 1 find a matrix B of rank 1 such that if I have some transformation, some linear transformation as being defined by B as its standard matrix of transformation, then the standard matrix of S composed with T is the zero matrix. So what do we want? I want a matrix of rank 1. So F. Okay. So B is a matrix of rank 1. Let's say that it has entries A, B, and C, and then 0, 0, 0, 0, 0, 0. Okay. Such that S composed with T of X is defined by some standard matrix of transformation C times X, where C is the zero matrix, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? But what is going to be the standard matrix of transformation of S composed with T? If B is the standard matrix of transformation of S, and A is the standard matrix of transformation of T, that means that B times A is equal to C. Okay, so what is B? B is A, B, C, 0, 0, 0, 0, 0, 0. and A is -3, -1, -2, 1, 0, 2, 2, 1, 0. Let's perform this multiplication, okay? -3 times A plus B plus 2C, okay? First row, second column, -A plus B times 0 is 0, plus C, and then -2A plus 2B plus 0 times C, right, which is 0. The rest of these entries here are just going to be zeros. And this matrix is the matrix C, which is the zero matrix. So basically the question is, how much are A, B, and C? What is the first row? What is the first row of B, right? Such that -3A plus B plus 2C, plus 2C is 0, -A plus C is 0, and -2A plus 2B is 0. But this leads me to another matrix, which is -3, -1, -2, 1, 0, 2, and 2, 1, 0, 0, 0, 0. You can row reduce this matrix, and you will get 1, 0, 0, 0, 1, 0, -1, -1, 0, 0, 0, 0. Okay. So from here, C is a free variable, A, B, and C is T, B is equal to T, A is equal to T. So basically A has to be equal to B, has to be equal to C. So if you want to give any matrix that satisfies this, let B be equal to 1, 1, 1, and then 0, 0, 0, 0, 0, 0, or any value for A, which has to be the same value for B and has to be the same value for C. Okay, the next question, let T be a transformation from R2 to R2 that rotates vectors clockwise around the origin by theta, then reflects them through the x-axis, then rotates them again by theta clockwise, and then reflects them through the y-axis. Okay? If the transformation T is defined by the standard matrix of transformation A, find the entrance of A. Find how much is A. Okay? So theta is not specified, theta is not given. Okay, so this is the unit circle, and we have the vectors E1 and the vector E2. So let's follow through this very big transformation T. That's actually a composition of four different transformation, and let's see where we're going to end up. So first of all, rotates vectors clockwise around the origin by theta. So let's say that this is theta. So after the first step, so this is theta. okay? Maybe because there are 4 different transformations, you can say that t is equal to s1, t of x is s1 of x, then to that one we apply s2 of x, then to this image we apply s3 of this, and then we apply s4, okay? So this would be s1 of e2, and this would be s1 of e1, okay? Then it reflects through the x-axis, okay? So this vector is being reflected over the x-axis, so we're going to be here. This is s2 of s1 of e1, and when you reflect, and this is the angle, it's the same angle, theta. We're going to reflect this on through the x-axis. This is going to be the angle theta here, and then you get, as you will see why it is important, s2 of s1 of e2, okay? So this part here is done, reflection through the x-axis. Then again rotates whatever is being obtained here is being rotated by theta clockwise. So basically this is being rotated by theta clockwise, and this one is being rotated by theta clockwise. So what do we get? We get that E1 is S3 of S2 of S1 of E1, and then this vector right here, which is the vector 0, -1, is S3 of S2 of S1, of E2. Okay. So this is also done. And then the last one is reflects these vectors through the y-axis. Well, when I'm going to reflect E1 through the y-axis, I'm going to finally obtain this vector here. Okay, so this is S4 of S3 of S2 of S1 of E1, and that's just the vector -1, 0. And this one, because it lies on the y-axis, it's not going to move from here. So this is S4 of S3 of S2 of S1 of E2. So again, I'm going to remind you, the standard matrix of the transformation is just going to be consisted of the columns that are the images of the unit standard vectors under the given transformation. So what happened to E1 after this transformation? E1 got transformed to -1, 0, and E2 got transformed to 0, -1. And that's the matrix A. Okay, if you want, you can also go through each different matrix of transformation and then perform this multiplication here of 4 matrices, and you have to end up with the same answer. Right, question 11. Let R2 to R2 be a transformation such that brings 1, 1 to 2, 1, brings -1, 1, -1 to -27, 13, and 2 and 3 to -27 and 13. The first question is T 1 to 1? Well, what does it mean for a transformation to be 1 to 1? It means that every different vector is being transformed into different vector. So it's impossible for the 2 different vectors to be transformed into the same into the same vector, and obviously that's not the case here, right? 1, negative 1 is not the same as 2 and 3, and yet t of 1, negative 1 is equal to t of 2, 3, which is equal to negative 27 and 13. This is just given by the condition, right? So hence t is not 1-to-1. Part B, express the vector 2, 3 as a linear combination of the vectors 1, 1 and 1, negative 1. Okay, so that means that I have some weights a times 1, 1 plus b times 1, negative 1 is equal to 2, 3, which means this vector equation is going to be written as a matrix equation 1, 1, 1, negative 1 times AB is equal to 2, 3. And how do we solve this matrix equation? Well, just we solve the system 1, 1, 1, negative 1, 2, 3, which if you subtract row 1 from row 2, you get 1, 1, 2 here. 1 minus 1 is 0, negative 1 minus 1 is negative 2, 3 minus 2 is 1, right? So from here, A and B, B is equal to negative 1/2, and then A minus 1/2 is equal to 2, so A minus 1/2 is equal to 2. From here, A is equal to 5/2. Okay, so 5/2 times 1, 1 minus 1/2 times 1, negative 1 is equal to the vector 2, 3. And then you can check whether this is we got the right solution or not, right? 5/2 minus 1/2, it's 4/2, which is 2. 5/2 plus 1/2 is 6/2, which is 3. Okay, so exactly what we needed. And finally, the question, is the transformation T linear? Okay, yes or no? Well, either we do what we did previously, when you have to prove, right, whether t sends 0 to 0, and then you take two vectors and multiply them by scalars and show that t of c1u plus c2v is equal to c1t of u plus c2t of v. But here the transformation is not defined explicitly, so we have to find another way to answer this question. So we have to look for a hint from what was done so far. Okay, I know that t of the vector 2, 3 is how much? Is given negative 27 and 13. Negative 27 and 13. Okay, but then t of 2, 3 is equal to t, the vector 2, 3 is expressed as this: 5/2, 1, 1 minus 1/2, 1, negative 1. Okay, which is equal to 5/2 t of 1, 1 minus 1/2 t of 1, negative 1. These two transformations are given, so that's 5/2. The transformation of the vector 1, 1 is 2, 1 minus 1/2. The transformation of the vector 1, negative 1 is negative 27, 13, which is equal to 5 minus plus 27 over 2, right? 5, right? 5 over 2 times 2 is 5, plus 27 over 2, and 5 over 2 minus 13 over 2, which is negative 4. And obviously this vector is not equal to this vector right here. Okay? Which means that this is not a linear transformation. Why? Because t of c1 times u plus c2 of v, when you're going to add these two vectors together, you'll get the vector 2 over 3, which by condition was negative 27 and 13. But in order this to be a linear transformation, this has to be equal to this condition right here. And obviously when we're going to solve that, it is not. So that is not a linear transformation.